Good afternoon to everyone. Today we have a slightly lighter program with a single talk by Yin Chen He, who will tell us about a roadmap for bootstrapping critical gauge theories. And as you know, you can just interrupt him if you want to make any question. So please go ahead.
Okay. So first of all, I would like to thank for these opportunities for me to talk about our recent work. So it's a collaboration with two wonderful bootstrappers, Junchen Rong and Ning Su. The paper was posted on arXiv several months ago. So if you are interested in details, you can check it online. Okay. So this is the outline of this talk. So I will start with a brief introduction of critical gauge theories, and then introduce the idea of the decoupling operators. So I will take a detour that I will try to make a connection between the 2D Westermann-Witten CFTs to gauge theories in higher dimensions. And although this detour is not necessary to talk about decoupling operators in gauge theories in higher dimensions, but I think it could be illuminating. So, and it was discussing it. And then after introducing this concept, then I will apply this into study critical gauge theories. In particular, we will focus on a prototypical type of gauge theory, that is scalar QED. I will show our results of obtaining a bootstrap kinks as well as bootstrap islands of the scalar QED. Okay, so in order to have everyone on the same page, let me give you a very brief introduction about critical gauge theories. So it refers to theories that have critical matter fields interacting with gauge fields. Typically, we can consider, for example, several flavors of gapless Dirac fermions or critical bosons interacting with a gauge field in certain Lie group like UN or SUN and so on. And the rough phase diagram of such critical gauge theories are known. For example, in 3D, we know if NF is large enough for a given gauge group, the theory will flow into an interacting CFT in the infrared. And on the other hand, if NF is very small, we know that the conformal fixed point will disappear through this fixed point collision mechanism, and then we will get the theory will flow to some non-CFT fixed point. So there will be some critical flavors separating those two fates, and we usually call the window that have CFTs lives in as conformal window. Okay. For the situation is slightly different. That is, for a given gauge group, the theory will indeed flow into a free theory if NF is large enough. And in between, we still get a window of CFT. And so that is what we know for. So even although the rough phase diagram is known to everyone, however, if you ask any quantitative questions, like what are the boundaries of the conformal window? And once the theory lives in the conformal window, what are the conformal data of these CFTs? Yeah, it's a little bit, it's pretty unsatisfactory that even after decades of efforts, we still don't know the answer for any gauge group, including U1 gauge group. So the hope is that maybe conformal bootstrap can really help us to answer those long-standing questions. And I also want to mention that as a condensed matter physicist, I care about those critical gauge theories is because they can describe quite many interesting phase transitions and sometimes even critical phases of matter that can be realized in condensed matter systems. So if we can solve those critical gauge theories using conformal bootstrap, then we can make predictions for several condensed matter experiments. Okay, that is the critical gauge theories. And the common wisdom about bootstrapping critical gauge theories is that people think maybe bootstrapping gauge theory is hard. And the difficulty is somehow built in the philosophy of the bootstrap. We know that the bootstrap use the self-consistency of the correlation functions of certain operators. And in gauge theory, the operators one would consider are usually gauge invariant. So if you write down the bootstrap equation, the gauge field does not appear in the bootstrap equation at all. So then the natural question is, how do you know we are actually bootstrapping a gauge theory? And what is a gauge group you are really bootstrapping? And let me be more concrete. Let's say a common setup or input of conformal bootstrap is that we input the global symmetries of the theory and then choose some operators to bootstrap. For example, if you consider Wilson-Fisher CFT, we know that the global symmetry is UN, ON, and you can choose, let's say, ON vector to bootstrap. And you can, and it is believed that with those conditions, plus some other assumptions like the number of relevant operators, then the Wilson-Fisher CFT is well defined. It's unique. So then it's then using, in principle, using Bootstrap, you can isolate Wilson-Fisher CFTs from all other theories. But the situation is rather different for critical gauge theory. For example, we can consider a bosonic gauge theory that has bosons interacting with a UNC gauge field. So now the global symmetry of this theory will be SUNF cross U1, which is independent of the color number NC. And you can choose operators like SUNF adjoint, whose its scaling dimension will be around 1 in 3 dimensions, which also has very little dependence on NC if NF is large enough. So then it's clear that in such setup, there's no sharp distinction between gauge theories with different color number. And this is so that's why people sometimes think that, well, in Bootstrap calculation, you don't really know what's the gauge group if you want to bootstrap gauge theories. But today in this talk, what I will try to convey is that this common wisdom is actually not true.
Wait, so sorry, I have a comment to make. Yeah. So I mean, there is a sharp distinction because you have operators in different representations depending on the number of colors in the gauge group, right? So like in particular in 3 dimension, you have multiple operators and they transform in different representations depending on what the gauge group.
That's true for some gauge theory, but actually here, let's say for this UN gauge, bosonic gauge theory, the monopole is always a singlet on the SUNF, so there's no sharp distinction. Even for many gauge theory, the representation of monopoles also has no dependence on the color number.
I would know, but I mean that also depends on the Chern-Simons level. I mean, you have to be careful. So
yeah, that depends on Chern-Simons. Yeah. But the point I'm trying to make is that for gauge theory, right, there always exists an infinite many different theories with different colors that has the same global symmetry. Even for the monopoles you are talking about, they will also live in the same representations. Yeah. But there is some distinctions, and that is what I'm going to say later. Yeah. Okay, so the important thing here is that there's a family of theories that with very same global symmetries and very similar operator spectrum. And actually, we know that in 2D, such situation is pretty common, right? we get like minimal models like Wedge-Witten CFTs. Those series have same global symmetry and very similar operator spectrum. But there we know it's not really, we don't really have any obstacle of bootstrapping those series, right? Like Eisen CFTs, like SU to level 1, out of its relative cousins. So, and there we know that the reason that, and we get bootstrap kinks are closely related to the very important structure of those CFTs. That is the null operators of 2D CFTs. Let me give you an example of this SU to level K Wedge-Witten CFT. We know that the global symmetry of this CFT will be SU to left times SU to right. And we can ask what are the operator spectrum of this Wedge-Witten CFT. So we can first look at the bifundamental that I will call 1/2, 1/2. And we know that the lowest operator in this channel will be a Kazamudi primary with this scaling dimension. And we can also ask what is the lowest operator in this 1/1 representation. If K is larger than 1, the lowest operator is again a Kazamudi primary with this scaling dimension. But when K equals to 1, this Kazamudi primary becomes a null operator. And the lowest operator in the spectrum will be a Kazamudi descendant, which is obtained by applying current on the vacuum. And the scaling dimension of this operator is 2. So now we can just plot these results, let's say with this plot those 2 scaling dimensions. And that's what we get. So you can say that here we get a sudden jump at SU to level 1, and this corresponds to nothing but the appearance of null operators in the operator spectrum. And this is what we obtained numerically, that we can say that now the numerical bounds is actually saturated by SU to level K for K large. And there's a kink with SU to level 1 precisely sitting in there. And this tells us that the appearance of this kink of SU to level 1 is nothing but we have a null operator appear in the operator spectrum. And as you know, for the 2D Eisen CFT kinks, people also figure out that it can be understood by the fact that you do have null operators appearing for the Eisen CFT. Okay, so this tells us that actually the 2D CFT kinks has very nice physical meanings. And on the other hand, you can also use this as an input to help you to bootstrap the CFTs that you are interested in. So now we hope to generalize this idea to higher dimensions, in particular for the critical gauge series. And to generalize it is to introduce a concept called a decoupling operator. So let me again use the example of this SU to level K Wedge-Witten CFT. So we can write down its correlation functions for some operators. Let's say for this lowest line operator in the SO4 vector. And the precise form of this correlation function can be found in textbook. So I won't really write it down here. The important thing here is that it's actually an analytical function of the Wedge-Witten level K. Although theoretically we know that the Wedge-Witten level should be an integer. But just from the perspective of the correlation function, there's nothing preventing us to promote this integer valued K to be a real value. Okay, so now we get this correlation function, and what we can do is that we just decompose this 4-point correlation functions into the global conformal blocks. And we can look at this 1-1 channel, and the lowest operator from this decomposition will be the Kazamudi primary that I just discussed in previous slides. And we can get this OP square like this. So you don't need to read it. The important thing here is that if you plot the OP square, you will find that it's always positive definite for k larger than 1. And it vanishes precisely at k equals to 1. And we know that that's because it's a null operator at k equals to 1. So that means that this Kazamudi prime, there's a Kazamudi primary decouples from the spectrum at k equals to 1, and this decoupled operator is the null operator for the 2D Western Witten CFT. Okay, and this is actually rather generic, that in many 2D CFTs, you can play this game. For example, for minimal models, people also figure out that the null operators can be thought as decoupling operators if it from this perspective. Okay, so let me just repeat what I said in a slightly more general language. So the decoupling operator is defined as following. Firstly, we consider a continuous extrapolation of a family of CFTs with the same global symmetry and operator spectrum. And then we continuously tune between the entire family of the CFTs. Like here, we tune the Western Witten level K. And at some special parameter point, there will be operators decoupled from the spectrum. And these are the decoupling operators. And in the context of 2D CFTs, in many cases, the decoupling operator just happens to be the null operators. Yeah, but then this can be, this notion of decoupling operator can be generalized to higher dimensions. And to make it work, actually, it'd be good to discuss a very interesting perspective of Western Witten CFTs. That is, indeed, the 2D Western Witten CFTs has a gauge theory description. For example, we can just consider SU and level K Western Witten CFT. And it is actually due to a gauge series with n flavors of 2D Dirac fermions interacting with a UK gauge field. For k equals 1, you can prove this duality exactly because the gauge theory is integrable, first noticed by Schwinger. For k larger than 1, it's not integrable anymore, but there's some evidences suggesting that the duality is correct. Okay, so the interesting thing is that indeed the null operator structures or the decoupling operator structures of WZW CFTs can be easily captured using this gauge series. So let's just do some very simple analysis. Let's look at the operator spectrum of this these two theories. So the global symmetry of this theory will be SU to left times SU to right. So and that's true for both theories. And we can ask what are the lowest lying operators in the bifundamental, that I will call it FL and FR. In the Western Witten theory, we know that the lowest operator will be a Kazamudi primary with this scaling dimension. Looking at the gauge theory, the lowest operator that you can write down will be a fermion bilinears that is gauge invariant. So here I use L and R to represent the flavor indices, and this C in red represents the color indices. So we know that in the larger limit, this operator has scaling dimension 1. This actually nicely matches this Kazamudi primary of Western Witten CFT. Okay, So we can continue to do this analysis. Let's say let's ask what is the lowest lying operators in the rank 4 tensor that are in the maybe I should call it rank 2 tensor that is anti-symmetric rank 2 tensor in both SUN left and SUN right. Again, in Westermann-Witten CFT, this operator, the lowest operator will be a Kazamudi primary with this scaling dimension. And we can, in the gauge series, this operator will be a 4 Fermi operators, schematically written as this. So, and here we need to anti-symmetrize the flavor indices. And because it's fermions, so then we need to symmetrize the color indices. So it's totally fine to do so. So then we get an operator with scaling dimension around 2. This again matches what we know of the Westermann-Witten CFTs in the larger limit. Okay. The interesting thing happens if we consider another representation that is a symmetric rank 2 tensor in both SUN left and SUN right. We know that in the Westermann-Witten CFT, the lowest operator at k larger than 1 is again a Kazamudi primary with this scaling dimension. And but at k equals to 1, the lowest operator, this Kazamudi primary becomes a null operator. And the lowest operator will then be a Kazamudi descendant obtained by applying current on this operator. And then we get its scaling dimension like this. So, and the interesting thing is that this this structure is nicely captured by the critical gauge series, by the gauge series. For example, if k is larger than 1, so you can write down a 4 Fermi operators that with the flavor indices symmetrized with the color indices anti-symmetrized. So the scaling dimension of this operator will be around 2, which matches the Westermann-Witten set. But if k equals to 1, you don't have enough indices to color indices to anti-symmetrize. And what you have to do is that you need to add 2 derivatives in the operators. Then you can make a legal operator in this representation. And this will gives you an operator with scaling dimension 4. And this again matches the Westermann-Witten CFTs. So you can actually continue to do this for higher level Ks to consider higher level representations. And the conclusion is that the null operators for any integer value of K can be simply recovered using the analysis from the gauge series side. And this tells us that the decoupling operators of Westermann-Witten theory can be simply understood from the gauge series. And this would then, and from gauge series side, we can easily generalize this idea to higher dimensions. For example, we can do this for a bosonic gauge series. Let's say we consider NF critical bosons coupled to a UNC gauge field. And let's just do it in 3D. For bosons, there's no dimension dependence. So you can consider the SUN adjoint. It will be a boson bilinears with this scaling dimension. And what's special is that if you consider a rank 4 tensor, that is anti-symmetric in both upper and down indices. For NC larger than 1, you can write down 4 Fermi operators that has both flavor and color indices anti-symmetrized. And this operator will have scaling dimension 2. But for NC equals to 1, not allowed to do so because you don't have enough color indices to anti-symmetrize. And again, you need to bring two derivatives to make a legal operator. And this will give you an operator with scaling dimension 4. You see, this structure is just is almost identical as 2D Western-Witten CFTs, except that you change the representations of this decoupling operator because we are considering boson here. Okay, so this tells us that the lowest operator of this NC larger than 1 is decoupled at NC equals 1. So this analysis carries over to higher NCs, and the price you need to pay is simply that you consider higher rank reps like this. And the analysis also applies to any gauge group you care about, like SON gauge group, USP gauge group, SUN gauge group, and so on. So, and let me just quickly summarize what I just said about decoupling operators. So it's a very simple observation that in gauge series, operators in specific representations are heavier, and that representation depends on the color number that depends on the color number. And this structure is very similar to the 2D Western-Witten CFTs. And there, the Western-Witten CFT plays the role of the color number NC. And for Western-Witten CFT, we can also, as I said, we can also analyze those decoupling operators just using the language of gauge series. Okay, but there's some also some interesting open questions. So in the example of Western-Witten CFT, we can literally write down correlation functions that are analytical functions of Western-Witten levels. So we can ask whether for gauge series in higher dimensions, are the correlation functions are also analytical functions of color number NC. If this is the case, whether the operators decoupled precisely at integer value NC, just like 2D. And we know that that is also more interesting question that we know that in 2D, the null operators has many profound features, like it can act as an operator that annihilates the correlation function. One can ask whether the decoupling operators in higher dimensions would have some of those properties, like in 2D. So I don't know how to make progress on those open questions. And in the rest of this talk, what I'm going to do is that I will stick with this phenomenological observations about the engaged series. There will be operators decoupled, and this can help us to uniquely determine what is the gauge group of the theory we are bootstrapping. So I think it's a good place to stop to say whether there are some questions.
Yin Chen, I have a question about the analyticity in N. So can you specify more precisely what you mean? Namely, we know from large N that in theories with no supersymmetry, for instance, not n equal to 4, the 1 over n expansion is non-analytic. Namely, the point nc equal to infinity is non-analytic. So most likely, I will guess that the correlation function as a function of n will be analytic in most of the complex plane, n plane, but aside from some branch cut and singular points that will be located somewhere that we don't know. So what do you mean that the correlation function is analytic in n? Can you specify better this point?
So frankly, I have no idea whether this is true. So what I'm trying to say is that in 2D we know, so as what I just said here, right? in 2D, we know everything about Western-Witten safety, right? And there we know the correlation function is an analytical function of the Western-Witten level K. And we also know that in 2D, those Western-Witten safeties is due to a gauge series with a UK gauge field. And then at least in 2D, we can safely say that the correlation function of this gauge series is an analytical function of the color group, right? And then the question that I want to pose is that whether this is true for gauge series in higher dimensions.
Yeah, no, I mean, for integrable models, I believe this is possible. In fact, for correlation function, I'm not sure whether this is still entirely analytic in K, but I mean, in 4D generically, I mean, this is highly to be not true. That's
okay.
Most likely it's not going to be true. Right?
Okay. Yeah. Thanks. Yeah. Thanks for the comment. Yeah. Okay. So let me move on. So I will change it here to numerical studies of this gauge series. So and in particular, I will use this concept of decoupling operators to bootstrap this scalar QED. Okay, so this is a Lagrangian of the scalar QED that we have several flavors of bosons interacting with a U1 gauge field. And the schematic phase diagram of this theory is that in 2 plus epsilon, this theory will flow to a safety everywhere for any NF. And for D equals to, in 3D, there's probably a region that the theory will flow to a non-safety fixed point. But for larger NF, it will be a safety.
Wait, so sorry, I'm confused by the statement in D equals 3, because I mean, people have done Monte Carlo studies of the scaling dimensions of monopole operators, and they match, like the, large N calculations, I think, for any value of NF. Like, so why do you think there shouldn't be a CFT for certain intermediate values?
I think the Monte Carlo results you were quoting the fermionic gauge series that was fermions covered with the U1 gauge field.
No.
I don't.
I'm talking specifically about scalar QED.
Okay. First of all, I'm not aware. So yeah, I don't know that Monte Carlo results, and the reason that I'm saying that there's likely to be a non-safety regions is due to this very intense study of this NF equals 2, that is this so-called deconfined phase. There are growing evidences suggesting that these phase transitions, a lot of Monte Carlo simulations, hundreds of suggesting that this is probably not a conformal fixed point. And there are many interesting proposals, such as this pseudo-criticality or complex fixed point. So I think that makes me to think that maybe the phase diagram looks like this. But you could be right that there may be, it could be safety everywhere for any NF. And this is actually the question that we really want to answer, whether there exists a non-safety region or it's just safety everywhere. Yeah, yeah. Okay, so this scalar QED has some interesting applications in condensed matter context. For example, when NF equals to 1, you know that this is actually there's this theory is due to O2 Wilson fission. And this duality sometimes is called particle vortex duality. That's why here I draw a phase diagram saying that it's a safety for NF equals 1. And for NF equals 2, as I said, it's deconfined phase transitions. They are growing evidence is suggesting that it's probably not a CFT, but very close to a CFT. And for general NF, you can find some condensed matter systems called SUN deconfined phase transitions that could realize this, are described by this scalar QED. Okay, so the scheme, the Bootstrap scheme we choose is to consider fermion bilinears that is in the SUN adjoint, and I will call this operator as A. So then we consider as 4-point correlation functions. So an important thing to know is that the OPE of two SUN adjoint looks like this. That means then we can numerically bound operators in these channels. So this S are just singlet, is just singlet. This adjoint is just SUN adjoint. And the last 4 representations are the rank tensors. Their naming convention is rather straightforward. For example, this AA bar just means that both upper and lower indices are antisymmetric. And this SS bar just means that both upper and lower indices are symmetric. And you may remember that the decoupling operator I talked about are just a lowest lying operator in this channel. So then a natural question is, what if we just numerically bound this operator? What will happen? So this is a numerical results.
Yeah, sorry, Yin Chen, can I make a comment on Shai comment? So just to be sure that we are on the same page. So I think I agree with Shai that for any NF, this theory will flow to a CFT, but what is not clear at the moment, as far as I know, is depends on the actual ratio between the Corti coupling and the gauge coupling. So this is another story, which is, so there is a regime of this ratio where certainly you go to a CFT, but there are other regimes in which we do not know what happens at low values of NF and whether there is a phase transition or not. So maybe this is what you had in mind. So for Shai, do you agree on that?
I mean, I thought there's, 2 possibilities, so it's like you have the analog of the critical ON model and the analog of the free ON model, except now with, I guess, critical UN model and free UN model, except now just with the gauge field. And so I would think there's just 2 possible CFTs you would potentially flow to. I mean, you also have these things called like easy plane, where you add, other terms to the potential, which might be what you're referring to. But I think just like vanilla, critical QED is expected to be a CFT for any.
Well, no, but the point you see that these theories are given NF are parameterized by a ratio which is E squared over G in the Yin Chen notation, and then this is actually a non-normalizable coupling. This is fixed. Okay, it's in fact unobservable in superconductors. I mean, Yin Chen might teach us. And the theory depends, the fate of the theory in the IR depends on the ratio. So it's not only, so at given NF, it actually depends on another ratio. And now it's true that for some values of the ratio, for any NF, you go to CFT. But for arbitrary value of this ratio, we do not know. So what we do know is that at large values of NF,
on the ratio. What do you mean that the theory depends on the ratio?
I'm not sure I agree. I think equals to because it's an irrelevant operator.
It's true that the fate, the RG flow depends on ratio. And I think in literature, we are very specific about what we mean by scalar QED. I forget the ratio. I think it's at G much larger than E. That is a theory. That is a fixed point we are talking about. If you switch the order, it can certainly flow to some other fixed point, and that's not the scalar QED we are talking about. And also just let me also make some comments about whether it's really whether there really exists a region for non-CFT. The really subtle issue for here is that even it is a non-CFT, its correlation length will be very large, just like the the well-known example of this 5D port model, right? The correlation length could be like 1,000 lattice spacing, can even be larger. And that means if you are doing Monte Carlo simulations, if your system is not huge, then you cannot really distinguish this non-safety behavior from safety behavior. That's really the subtle issue for Monte Carlo simulations. And that I think this should be answered by a more algebraic approach like conformal bootstrap. Yeah. Okay, so let me just go back to my our numerical results. So the first thing that we did is to bound this decoupling operator, and this is a result for in 3D. So here you can see that there's a very sharp kink appears in the numerical bound, and as NF goes to infinite, this jump precisely happens at the the scaling happens at what we should expect for the scalar QED. So this results tells us that this idea of decoupling operators is probably working for bootstrapping this scalar QED. And the numerical bounds captures some essential physics of this operator decoupling. However, if you after we did more careful analysis, what we realize is that this kink itself is not scalar QED. For example, we can look at the larger NF limit. That here I plot the dashed line I plot here are the larger results for the scaling dimension of the SUN adjoint. We can see that there is a considerable discrepancy between this kink and this larger results, and then the discrepancy is larger than 1 over NF. So that means, yeah, this kink cannot be the scalar QED, although it's pretty close, but not. Okay. That's also the case if we consider 2 plus epsilon dimensions, that you can say we still get a kink which goes in the infinite coincide with scalar QED, but at finite n it has quite large discrepancy. But the cool thing here is that this operator decoupling is still captured by numerical bootstrap, and the likely scenario is that the abelian gauge series are living in the region here after the kink, while the non-abelian gauge series are living in the region before the kink. So that means that if we just simply add a very mild gap in this decoupling operator channel, we are able to kill all the non-abelian gauge series and then let's try to bound other operators to say whether the scalar QED would appear. So, and it turns out to be the case if we consider 2 plus epsilon dimension. For example, here, if we consider 2.1 dimensions, and we bound the SUNF singlet. If we don't add any gap in this decoupling operator channel, the leftmost bound is what we obtained numerically. We can see there's a kink, but this kink is likely to be something like Wilson Fisher. But once you add a pretty mild gap in this decoupling operator channel, and then you see the numerical bounds are improved significantly, and then we get a kink which matches the 2 plus epsilon results of scalar QED. This green dot just 2 plus epsilon results. And this numerical bound as well as a kink is not sensible to the gap we add. For example, here, indeed, I plot two different gaps with like 0.2 and 1.2 and 1.7. You can say that, yeah, you cannot see any difference. There's no any visible difference between those two, between the bounds obtained by two different gap conditions. And those gap conditions are still considerably large, considerably smaller than the physical gap of the scalar QED. Okay, so this result tells us that, yeah, it's pretty nice that we have scalar QED appears as a kink, and we just add a small, pretty mild gap, and in the decoupling operator, and it's stable against the change of gap. Yeah, this result is nice, but if we the most interesting question that we care about is of course 3D. But disappointingly, what we find is that this kink, for some reason, disappears as we move towards 3D. Here we choose NF equals to 100, which is pretty safe to give us safety in 3D. And again, in 2 plus epsilon, you say that we get a kink, which nicely agrees with 2 plus epsilon dimensions. But in 3D, you say this kink no longer exists. And the numerical bounds are actually pretty far away from the large NF results. And you can see how the kink disappears. For example, in 2.4, we still get this kink, but it becomes rather weak. And in 2.7, you don't really see this kink. This kink is actually this one. It's related to the decoupling operators. Yeah. So we don't understand why this is the case. So one reason we certainly know is that the numerical convergence becomes worse and worse as we go to higher dimensions. Here, for example, you can say the discrepancy between different lambdas becomes larger and larger as dimension increases. But we don't know whether that's the only reason, or there are some more important reason that we need to make this kink disappear. But yeah.
Well, okay, so I mean, oh, sorry.
Okay.
Can I make a comment? If that's okay. So, I mean, to me, I would think maybe the reason why the kink is disappearing is that for QED, 3 dimensions is qualitatively different from any dimension other than 3 dimensions, because in 3 dimensions you have Chern-Simons level, which can take any value, and in your current setup, you're not fixing the value of the Chern-Simons level. So, like, who is to say that it's like the K equals 50 theory, which is like really saturating the bound in 3D, but you just don't have an analog of that the moment you go below 3D. And so that's why you're just getting some smooth thing. And so it's very important that you input the Chern-Simons level. I mean, a related comment is that also you have monopole operators in 3D and you don't have them the moment you go away from 3D. But that might be of lesser importance.
Yeah, I think the monopole reason is not that important. So indeed, you can play this game for other gauge group. Like one thing we played is for the USP2 gauge group, that SU2 gauge group, and we bootstrap USP2N operators. And the results is rather similar, that in 2 plus epsilon, we get the kink of QCD, which matches 2 plus epsilon, but in 3D, the kink disappears. And there, for SU2 gauge field, then there's nothing like monopoles and so on. And so that means the monopole is not really makes this happen. And for Chern-Simons, I totally agree with you. 3D is special because of Chern-Simons. Yeah. So, but I don't know whether that's the only reason, or there are some other things that I tend to say there may be some other things happen. Not just Chern-Simons, but yeah.
Well, yes, I mean, one thing you guys might find useful is that if you already know the scaling dimension in this large flavor expansion for zero-turn Simons level, it's very easy to get the answer for non-zero-turn Simons level. Because at leading order and large flavor, they're related quadratically. So like there's some approximate symmetry in the large NF expansion, such that you can just like, instead of writing like 1 over NF, you can write like 1 over NF plus something like plus K times pi or something. And so you can just kind of check explicitly, you know, how this is comparing to your plot.
Yeah. So I think the I cannot remember it exactly, but I think the Chen-Simons would be for the Chen-Simons theory. It will live on the right of the scalar QED. I mean, it's the scaling dimension of SU adjoint will be larger than the value of scalar QED. It's very easy to understand in the situation that Chen-Simons level is infinite. You know, that is just a semi-classical one. And that has scaling dimension. Let's say SU adjoint will have scaling dimension 1. And we know for K equals to 0, the scaling dimension is always smaller than 1. So yeah, that means, yeah, if you just move from left to right along the x-axis, you will first meet scalar QED and then Chen-Simons. Yeah, that means, in other words, the Chen-Simons would not really make this scalar QED disappear.
So I would be careful about using this intuition from the large K limit because in theories with supersymmetry in 3 dimensions, for instance, with maximal supersymmetry, you can look at theories parameterized by the Chen-Simons level, and you find that it kind of has a curve where, so it's like, while it's true that like the very large K theory is like far away from the boundary, the theory that's closest to the boundary is like some finite value of K. So it's neither the biggest nor the smallest.
Okay.
And so, I mean, I don't know, that could be different without.
Yeah. You're right. Yeah, I totally agree that Chen-Simons could be a reason, but yeah, just what I'm trying to say is that I believe that's not the only reason, or that's not the most important reason. Yeah. Okay, so now let me move to the last part about this bootstrap islands of the scalar QED. Okay. So, and indeed here, we can, for this section, indeed, we can carefully deal with the Chen-Simons theories. So, although probably I will not really talk too much, but
is there some way for you to impose parities so that to kill this discussion of Chen-Simons?
Yeah, we can. Yeah, I mean, we can bootstrap conserved current. Yeah, then it's exclude the Chen-Simons. Yeah, but we haven't done it. I'm always eager to do that.
Okay.
Okay. So but we all know that for Wilson Fisher, people can get bootstrap islands by imposing some conditions and consider mixed correlators. Okay. And the philosophy of getting a bootstrap island is slightly different from getting a bootstrap kink. We know that in order to get an island, what you need to do is to exclude all other crossing solutions of bootstrap equations. That's how you can get it isolated into an island. And the bootstrap equation we are considering are the 4-point correlation functions of SU adjoint. So then the first question we should ask is, what are the theories are consistent with these bootstrap equations? So here is a list of theories that we can identify that includes the Chen-Simons theories in 3D. Okay, and now in order to isolate it, we at least need to find conditions exclude all other theories, but leaves scalar QED intact. So now you can say that this list is actually pretty large compared to Wilson Fisher. So this is actually another reason makes bootstrapping critical gauge theories hard, because the theory space are much more dense. Okay, and there of course several ways, like you can bootstrap conserve current to impose parity symmetry to exclude transaminase series. Those are certainly interesting directions to pursue. And the first thing that we did is still stick with this correlator and ask, is it already enough for us to exclude all the theories we listed here? And it turns out to be the case. So let me just, I will not walk through every single series that I listed here. I will just give you an example of this so-called O2F Star, which I think is probably the most illuminating one. So, so recall that the scalar QED is just a critical bosons interacting with a U1 gauge field. You can certainly replace this U1 gauge field with some discrete gauge field, right? By doing this, then we get a theory that in condensed matter literature is called O2F Star. So that's nothing but Wilson-Fisher, right? And the difference is that you just need to consider operators that are invariant under this Zn gauge field, right? And but if you look at the operator spectrums, you will see they're rather similar, right? Like the lowest operators in each channels, they are more or less the same up to some 1 of NF corrections. That's also the case if you include the transaminase theory here in 3D. Okay, so now the question is, how can we exclude this theory, this O2F Star? And the thing that would help us is actually there's some interesting features in the operator spectrums, which is a consequence of equation motion. And this we can actually use that to exclude this O2F Star as well as transaminase. So here I will not explain why it works for transaminase, but in our paper we have commented on that. So let me let's just look at the larger NF Lagrangian of this scalar QED. So here what I have done is to introduce auxiliary field, which is what people typically do in this critical bosonic theories to replace the quantity terms. Of course, you still get a sigma square and a Maxwell term, but they are irrelevant, so you can drop it in the IR in the larger NF limit. So now you can simply write down the equation of motion of this Lagrangian. For example, you can get, say, a phi squared equals to 0. And this equation of motion is actually known that in the context of Wilson-Fisher. And what's special for scalar QED for gauge theory is that you get another equation of motion that is a gauge current equals to 0. In other words, the gauge current is being gauged. That is also expected, right? So now the idea to use equation of motion is that in the operator spectrum, any operator proportional to the equation of motion should not exist in the operator spectrum. This is actually was known in the context of Wilson-Fisher, like any operators proportional to phi square should be disappear. That's why in the Wilson-Fisher, in the singlet channel, the operators will be like the lowest one will be 2, the second the lowest one will be 4, and so on. You don't get operators with scaling dimension 1 or 3 and so on. Yeah, and in the context of gauge series, it has also been discussed. I think the first time I saw this is probably in a paper by Shai and Tufu, that they talk about this in the fermionic gauge series. So, okay. And what we can do is to use this feature to and then ask what can it make some difference in the operator spectrum. So unfortunately, this operator will not appear in the OPE because yeah.
Sorry to interrupt you. I missed the point. Yeah. Can you repeat how how can you neglect a leading order in NF the usual correction coming from the phi propagators, the bubble, the the famous large N bubble? I mean, the equation motion for sigma should be much more complicated. So you are neglecting the scalar bubble contribution. How could you?
So are you asking about this Lagrangian or why the operators would disappear? So okay, I'm sure there will be experts in the audience.
No, what I want to say is that you can expand around the constant fluctuation, right? The wave of phi, right? But then the fluctuation itself will enter as a contribution to the sigma phi, I mean, to the sigma effective potential in a non-trivial.
Yeah, but he's talking about large N, where these fluctuations are
the usual way in which we use large N to compute.
Yeah, I think it has been written in several papers, although I haven't really gone through the calculation by myself. So the claim from the paper, let me just quote it, is that if you just you can literally write down these operators or these operators, right, or any operator proportional to it, and then you calculate its correlators using large N expansions. And I think the claim is that the to leading order, probably to any order, the correlation functions will be exactly 0 in the perturbation scheme. That was a claim. I think maybe someone in the audience can also comment on this, but that's what I learned from literatures. Yeah.
Okay, never mind. Thanks.
Yeah, I'm actually also confused about. So you write these two equations, but they have a different status, kind of. So I'm a little bit confused. Maybe you can comment. So the first equation, okay, from my point of view, doesn't look so surprising because you just replace phi squared by sigma. So you throw out phi squared, but you brought in a new field sigma, which has a different dimension. So okay, it just means that certain fields change dimension. Yeah, but the second also equation, yeah, I'm kind of surprised what's the meaning of the second equation, because this is the current. So like if I were at finite N, I would just say that the current is a descendant of F mu nu. Yeah. But here you say it's not a descendant, you just set it to 0. Well, it's just a different perspective, right? You can say it's a descendant of F mu nu, then whenever you have this operator, you replace it with F mu nu, right? That means that they're the same operators. Or another perspective, you just well, not with F mu nu, with the derivative of F mu nu. Yeah. So, but you are not going to say that the correlation functions of this guy actually are going to vanish somehow miraculously. Well, this in the IR, this guy is not well defined, right? It's just an UV operator. Okay, so you just say that it becomes a if you say it's equivalent of saying that it becomes descent, then I'm less confused. Okay. Okay, sounds good. Yeah. I guess what the claim is that I mean, usually when we are trying to get some sense about the operator spectrums, right, we just write down those UV operators, right, and we know which is primary, which is a descendant, right? We know that on the RG, those operators will be adjacent, right? But there's still a primary operator with a very close scaling dimensions. There will be descendant with very close scaling dimensions with the UV descendant and so on, right? And what I'm trying to say is that when you are doing this analysis in the UV, you need to you should delete some operators. And those operators will be proportional to the equation motion, just like the Wilson-Fisher, right? When you write down, if you just consider SUN ON singlet, right? You don't have operators with scaling dimension 1.
Okay, so I mean, maybe I can make a point to clarify. So there is a difference though between these two equations. So the equation on the left is the statement, as Slava was saying, that in the large NF limit, you basically are replacing phi squared by sigma. So in some sense, you're replacing phi squared by its shadow operator, because it'll have like roughly dimension 2 instead of roughly dimension 1 in 3 dimensions. But the equation on the right, the spectrum actually remains exactly the same, because what happens is that you replace like what would have been the U1 current instead by F mu nu, and they have the exact same quantum numbers in 3 dimensions. because they both spin 1 and they're both dimension 2. And so that's why I don't think the spectrum actually changes in that sense.
No, the scaling dimension are different. This one has scaling dimension 2, but the operator you want to replace is the descendant of f mu nu. That one has scaling dimension 3.
No. But I mean, but like the correct statement is that you're replacing the current by f mu nu. I mean, these are like, I mean, that's
no. The correct statement is you replace current by the partial mu f mu nu, right? That operator has scaling dimension 3. You don't, yeah. That's a statement, not f mu nu. For f mu nu, you know, so for f mu nu, you know, the parity symmetry is different, right? For f mu nu, you need to contract with the epsilon tensor, then you get a parity odd operator, but this guy is parity even.
Okay. I mean, as far as I understand, like the only change in like single trace operators in the large N limit for QED is that you replace the current by f mu nu, and those are the exact same quantum numbers, and there shouldn't be any other change.
No, you don't replace it by f mu nu. You replace by descendant of f mu nu. That is what Slava said, right?
You know, okay, but I guess I'm confused by this equation on the right hand side, because my understanding is that in the large N limit, the only change that happens is that you used to have a U1 current, which has dimension 2 and spin 1, and then instead you have f mu nu, which also has dimension 2 and spin 1, and so that should be
no. But parity is different.
You're saying like, okay, so you're saying the parity between f mu nu as well as the versus the current are different.
For f mu nu to get a spin 1 operator, you need to contract it with epsilon tensor. That changes parity.
I see. Okay, so you're saying you're going to use the fact that the parity is different.
Yeah. For Chen-Simon theory, that's totally fine. But for scalar QED, there's a sharp distinction. Okay, so we can just do this analysis to consider SUN adjoint L equals to 1 operator for this O2F star. And the second lowest operator will be schematically written like this. And we just have this SUN adjoint times this gauge current, and its scaling dimension will be around this. And it's totally fine because for O2F star, we don't get to the second equation motion. Yeah, and for scalar QED, the situation is different because this one is no longer exists, or in another perspective that in alternative perspective that Slava was not, should replace this operator with the derivative of f mu nu, which will also make this operator heavier than the one in the O2F star. No matter which perspective you take, the conclusion is that the lowest operator in this channel then will be higher. And indeed, the lowest operator will have this scaling dimension. For example, you can write down it like this. You can also write down this operator, but replace it with the derivative of f mu nu. Yeah.
No,
so
I'm sorry, I don't understand. So why are you writing for QED J mu equal? I mean, you told us that you're not supposed to write this operator in QED because it's a descendant, and yet you write J mu for QED. I'm confused.
Sorry.
As we discussed, J mu in QED is a descendant.
That's flavor current. Here it's a flavor current.
Ah, it's a flavor. Sorry. Yeah. I take it back.
Yeah. We are not able to directly use this fact because it's in the single channel. In the OPE, it doesn't appear. That is a pretty unfortunate situation. Okay. So now we say there's a sharp distinction between those two theories. If you just do the analysis for Chen-Simon theory, you will reach that the lowest operator will be same as the O2F star because you can just replace it with the topological current here. Because their parity is not an issue, but here, for scalar QED, we have parity symmetry, so that operator will not appear in the OPE. Okay, so this is our numerical results. again, in 2 plus epsilon dimensions. So we add those mild gaps, right? As I explained, like the mild gaps in decoupling operator to kill the non-abelian gauge series and so on. So now, and we bound this second lowest operators in this SUN adjoint L equals to 1 channel. So now you see that there's a very sharp spike, and with scalar QED living on the edge of this spike. And on the other hand, this O2F star just lives after the spike. So now you see that this gap feature, although it might be a little bit complicated to analyze, but at the end of the day, you say that this gap feature is nicely captured by numerical bound, numerical bootstrap. So and now what we can do is that we just add a mild gap in this channel, and then we can get an island like this. So here is an island, again, in 2 plus epsilon dimensions with those gaps imposed. It's a single correlator bootstrap. So you see that the gap we imposed are indeed pretty mild compared to the physical gap that we have here. And but there's always a but that this island again does not survive as we goes to 3D. Again, it could be a convergence issue that we have no way to solve it. On this, you guys find very good new functional to deal with it. But eventually, we find that actually this island would also exist if we try to plot the parameter space in other operators, not just a singlet. For example, we can consider, we can try to bound this rank 4 tensor. Just remind you that this refers to that both upper and down indices are symmetric. If we bound this channel, we also get island, and it seems that the island becomes smaller and the convergence is better. So again, we impose those mild gaps. And the nice thing here is that this island would then survive in 3D. So this is what we append in 3D. So again, this is a single correlator bootstrap. We just impose 3 gaps, 1 more compared to Wilson Fisher. And those gaps are rather mild compared to the physical gap in the infinite and lit. And as I explained, those gaps has clear physical meanings. Like the first one is a decoupling operator. We needed to exclude all the non-abelian gauge series. The second one comes from the equation motion. We need to exclude it Chen-Simon series, as well as the O2F Star, that is Wilson Fisher. So now by doing this, we can we get a pretty we get an island for large NF, like NF equals to 1,000 and 100. And this island, however, does not survive in the for a smaller NF that we care about, like NF equals 20, and they just gets connected with the mainland. And we think it's likely to be a convergence issue, because here we really just using single correlator, right? You should not expect we can solve scalar QED with just a single correlator bootstrap. And one thing that we have noticed is that the convergence becomes worse as NF becomes smaller. For example, here for NF equals to 100, we are not able to get an island with lambda equal to 90. But for NF equal to 1,000, the island simply appears even for small lambda like 19. But for NF equals to 100, we do get island if we increase the lambda. That tells us that the convergence is an issue for large NF. So we hope that So maybe the mixed correlators, like we mix this rank 4 tensor with this SUN adjoint, could eventually drastically shrink the island and also get to the island for smaller NF. And we are currently working on this. Okay, so let me summarize. So so we have provided a very simple and workable answer about how to detect gauge group in a Bootstrap study. The method is based on a very simple phenomenological observations that we will call it decoupling operator. And I think at least at the phenomenological level, it's a higher dimensional reminiscent of null operators in 2D Western Witten safety. I don't know whether there are some deeper theoretical thing to explore, but on the level of practically, we can just use this to bootstrap critical gauge theories, like to distinguish gauge group. And as an application, we have obtained scalar QED kinks and islands in both 2+ epsilon and 3 dimensions. The results are not perfect. We haven't really solved the scalar QED for smaller NF in 3D, but I think it will be promising that if we do mixed correlators, like to mix SUN adjoint with a rank 4 tensor. It's a bit terrifying project, like the bootstrap equations is already very complicated, but I think we are running on the right track to tackle this problem. Okay, thank you.
Thank you, Hin. Are there more questions?
Perhaps, can I just ask, I didn't understand why adding the rank 4 tensor as an external operator is the natural thing to do. Is it just because that's where you saw the island, or?
Yeah. And maybe another thing which we do not really understand is that the feeling is that if you add a more high rank operators, then you may say more structures about the global symmetry. That's another feeling we have, right? But yeah, I don't know how to really make this precise, right? And the other thing is that we know this operator is relevant, right? There are only 3 relevant operators in this theory, right? So then the natural idea is that we should involve those low-lying operators, right?
Wait, sorry. I mean, I'm not sure I agree. You said, because like the monopole operator is relevant at small NF. I mean, for instance, at NF equals 1, due to particle vortex duality, you know, it's just like basically a a free theory.
Yeah, I agree. Yeah.
So there should be more than 3 relevant operators.
I mean, for larger NF,
Sure, but the case you're ultimately interested in is small NF. And I mean, I guess like a related comment is that you're not using the full symmetry of the problem, because the full global symmetry is SUNF cross U1. You're only using SUNF. And so I would think that like, if you're going to do mixed correlators, you should definitely include monopole operators. So you're actually including.
So that's certainly a thing worth exploring. But the reason that I am not inclined to a mixed monopole operator, there are several reasons. First is that we know for larger NF, the monopole are pretty heavy. We know that so practically that won't help us in bootstrap calculation. We want to avoid bootstrapping heavy operators because the numerical convergence is really bad. The constraining power is very small. And the second reason is more technical. If you just mix monopole operators, you will not find a very interesting crossings or interesting OPs between, let's say, SUN adjoint and monopole in this case. For fermionic gauge theory, you certainly have, but for this case, because monopole is a singlet in SUNF, so the crossing is trivial, which means that actually on the level of bootstrap equation, you can just write down the trivial answer to satisfy the bootstrap equations. Then that means if you really want to mix monopole operators, that's not the only operator you have to mix. You need to involve more and more operators to get the crossing, to get the OPE non-trivial, then you can make the multiple work. So I think that one of the most promising thing to incorporate all the symmetries to bootstrap topological current. Yeah, you know, for that operator, it's a conserved operator, and it's that, yeah, dimension is low, and it captures the U1 symmetries, and you get pretty non-trivial crossings, including that you can exclude parity symmetry. You can exclude consignments just by imposing parity symmetries. That is certainly very promising direction, yeah, that I'm eager to pursue. But right now, I think it's also promising here that to mix this rank 4 tensor, although it's rather complicated, but I think we have a pretty good chance to make it work.
More questions, comments?
And what would be the simplest setup which would be sensitive to the gauge field equations of motion?
I think the one we analyzed is probably the best one, the most generic one. For U1 gauge group, as I said, there are other ways, like in particular, you can involve the topological U1 symmetries, right? That is very sharp. But
this setup that you just wrote here was not sensitive to the. I'm not sure if it was. Yeah, so this setup was not sensitive to the right-hand side equation, right? As I initially was mistaken. So I was talking about the fact that this guy on the right, phi k, d mu phi k, that it's a descendant of f mu. What would be the simplest setup sensitive to that equation?
It's probably you want to consider current, U1 current, right? I'm not sure whether there you could get this OPE, like you just declare there's a U1 symmetry in the theory, and then you mix the current of that U1 symmetry. You probably can.
It would be the topological U1.
Yeah. For the scalar QED, that will be topological U1. Yeah. But for O2F Star, that will be just the phase U1, right? That. Yeah. And for consignments, that will also be topological U1, but you know there's a parity symmetry that you can make use of. For this, I think that is very ideal setup. Yeah, for U1 theory, right? But if you ask this question even harder, like generically for gauge theory, right? How do you know this equation of motion? Then if it is a non-abelian gauge theory, this equation of motion is not even gauge invariant.
I know.
So then to make use of it, then I did some analysis for several gauge groups, like USP gauge groups and so on. And turns out that the feature that I just explained here also carries over there. Okay. And that means it's a universal feature that you can use to distinguish gauge series from any other non-gauge series, including consignment series. Right? Yeah.
Can I just ask a clarification? So the difficulty is because in your OPE, you don't have SUN singlets with spin 1, that sector is not accessible to you.
Yeah, exactly. And a side comment is that you can certainly consider higher operators. For example, but they're you can consider other operators, but they are pretty heavy. So then probably this operator will not give you much constraining power, right? If the external operator are very heavy, then just a GFF would have a very high, will have a heavy operator in this channel. Then you won't be able to distinguish. So then what I was trying to say is that this feature will not then be detected if the external operator are heavy.
So if you just take, yeah, okay, sorry. What would be the simplest OPE that would be?
You can, for example, you can consider you can consider mixed correlator between two SUN adjoint, right? The lowest one and the second lowest one, and there you will have this.
I see.
Kind of appeared, but the point I was trying to make is that there, because the external operators are heavy, that this feature is very difficult to detect. Yeah, we tried that. We tried to mix those two SUN adjoint, but it doesn't work. Yeah, we have tried a lot of things. Yeah, including various of mixing. Yeah, the only two things left we haven't tried is to mix the. There are three things we haven't tried. First is mix multiple operators, although I kind of think that may not work. And the other thing is that we can mix the topological current. That is probably the best shot. And the thing that we are working on is to mix the this SS bar, this rank 4 tensor, which I think we have pretty good chance to make it work here.
Good luck.
Okay, so let us thank Finn again.
Yeah, thanks.